Welcome to Maths with EJD. Just like I told you, this video is about a Python code for a profit maximization problem. So the same problem we solved in the previous video using graphical method. Now I'm going to show you how to use Python to deal with that problem. Again, the problem statement is what you see there. A company specializes in the manufacturing of two products, wristwatches and pocket watches. To produce each unit of either product, the company must allocate time on two machines, machine one and machine two. Each unit of a wristwatch contributes $3 to the company's profit, whereas each unit of a pocket watch contributes $5. So the company faces constraints based on the available machine time. Machine one can operate for a maximum of 8 hours. Each unit of a wristwatch requires 1 hour of machine one's time, while each unit of a pocket watch demands 2 hours. Similarly, Machine 2 has a maximum availability of 12 hours. So for this machine, each unit of a wristwatch requires 3 hours, and each unit of a pocket watch requires 2 hours. So it is essential to note that the company cannot produce negative quantities of either product. Therefore, the production levels of wristwatches and pocket watches must be zero or positive. So the company's task is to strategically determine the quantities of wristwatches and pocket watches to manufacture, ensuring that the production remains within the limits set by the machine availability while simultaneously aiming for the highest possible profit. And you remember from that question, we discovered that the company should actually produce two wristwatches and three pocket watches in order to make $21 maximum profit. Okay. So this is in two now. You see how to represent the problem mathematically, which we did before. So in that other case, I used my x1 was W, that's W for wristwatches, and x2 was P, which is P for pocket watches. So we have to maximize Z equals 3x1, all right, plus 5x2. So, and these are the constraints. X1 plus 2x2 is less than or equal to 8, or what I call W plus 2P less than or equal to 8, or and then 3W plus 2P less than or equal to 12. And then you have the non-negativity constraint that the number of watches. So if X1 is number of watches produced and X2 is number of wristwatches produced, and X2 is number of pocket watches produced, you cannot have negative production. The worst you can have is zero production, not producing at all. So that's why you have the non-negativity constraints. And, to put that in Python, right, you need NumPy for numerical Python. You need Matplotlib. So Matplotlib here, I need it for the graphing because Python can also do the graphing. The other time I did the graph manually, I also showed you how to use Desmos to plot the graph in a very easy way. And then for the linear programming, now we need scipy.optimize. Scipy is scientific Python. So one of its functionalities is optimization. So and inside optimization, you have a function called linear programming, linprog. So in line 6 now, here you are defining the objective function. So the objective function is 3x1 plus 5x2. So here now, and it's a maximization problem. So when you negate it like that, you're actually making it into a minimization problem. So you can turn a maximization problem into a minimization problem by just by multiplying through by minus. Okay. So here now, instead of 3x1, 5x. So I'm having something like minus z equals minus 3x1 plus 5x2. So that we extract the minus 3 and minus 5 and then thereby turning it into a minimization problem. So you see 3x1 plus 5x2 becomes maybe not even z now. Maybe you can just call it something like w, w now is equal to minus z, okay? So when you negate it, you turn maximization into minimization problem. And then you extract minus 3 and minus 5 from that. Then the coefficient of the inequality constraint. So looking at the inequality constraint, now you have coefficient of x1 is 1, coefficient of x2 is 2, right? And then the coefficient of 3x1 is 3, coefficient of x2 rather, coefficient of x1 is 3, coefficient of x2 is 2. So here now you define coefficient of the inequality constraint. So C is for the objective function. A is for the coefficient of the inequality constraints. So if you have more constraints, you just keep on listing them out like that. Now, the right side, so there are three sides. You have the objective function, which is C. You have the coefficient, a matrix of the inequality constraints, and then you have the right side of the inequality constraint. The right side will now be your 8 and 12, this 8 for the first one and 12 for the second one. And that is what is defined here. B is 8, 12. Now, Then we also need boundaries, right? Bounds for each variable. For instance, x1 is greater than or equal to 0, x2 is greater than or equal to 0. So, and the way to define that is what you have in line 18 and 19. So for the x bounds, you have 0, comma, none. That is, it can be 0 upwards. It has no boundary at the top. But if it is something that is bounded from the value can only be between 0 and 10. So instead of none, you have 10. So now in 19, you define the bound. So you have x bounds, comma, x bounds. Okay. And then in line 22, you have this is where the linear programming is actually happening. So solve the linear programming problem. So then that's where you now call the linprog from scipy.optimize. So, and there you feed it with the objective function, you feed it with the A, and that A is actually like A underscore UB, subject to the A underscore UB and B underscore UB, that's your B. And then you need the bounds, and the method you are using is highs method right here. And then in line 24, you extract results if optimization is successful. So now this is very important because sometimes you won't always get some optimization problems. So I'm going to see in the next topic I'm going to take, right? There are some exceptional cases where you will never find solutions, or you find more than one solution to your problem. So in that case, so it's not in all cases that you're going to get solutions. So that's what we need, this condition now. If result dot success, this result now. So if result dot success, so you have xi optimum, x2 optimum equals result dot x. That means that the best value of x1 and the best value of x2 will be extracted as result dot x. The maximum profit will now be minus result dot fund. Now this minus result now is because you have changed maximization problem into a minimization problem here. So you have to, when you get here now, you have to negate whatever you get so you can get it back in the right sense. So you have to negate to get the original maximization objective value, right? So then plotting the feasible region and optimal solution. So now I also need to show the plot. That's what I'm doing here. So to show that now it's more or less like you are solving just like what I did the other time. Yeah, x1 now we want to plot it from between 0 and 10. Range of x1 values for plotting. So and then so you can solve x2 constraints, x1 constraint. So this is more or less like what I did by solving the simultaneous equation to get 2 and 3 for x1 and x2 correspondingly. Then we are now plotting all of that graph. And so every other thing you see here is for plotting the graphs. Of course, we also want to show the label, like L1 is this equation, L2 is this equation in different colors for easy identification. Then we also want to see the maximum value and all that. The feasible region, we want to shade it in gray and all of that. Then we have the proper plot now. Now we need the optimal point where x1 is equal to 2, right? And x2 is equal to 3. And then we want it to be in red dot or something like that. That's what this R naught means. And then all this other one is just to make the graph look great. Okay. So by the time we run this in one blow, we get our result. So it takes a bit of time. So depending on how complex the problem is, it may take a lot of time sometimes. So you see the graph right now, just like what I plotted the other time. So you see the feasible region now, it's shaded in gray. So the optimal solution is this red one, which corresponds to that 2, 3 we got. So, and the result is clearly spelled out here. Optimal solution, X1 is 20. That's number of wristwatches should be 2.0, whether it is 2.0 tons or 2.0 dozens, anyhow, whatever unit you're using. And x2 for pocket watches is 3.0. And if that happens, the maximum profit is going to be Z equals 21, which corresponds with what we did in the previous video. So, I mean, you can use Python to deal with all these things. Interestingly, there's just like I think in the first or second video on linear programming, I also told you that I think there's a specific Python library for linear programming, but we can also use scipy.optimize, which we have used here. So if there's a reason to ever use that, we'll come across it as we progress in this linear programming journey. Thank you for following up till this point. If you have not subscribed to this channel, be sure to do that. Okay, be sure to subscribe and hit the notification bell so you can always get alerted each time a new video is released. Don't forget to also like and comment. Comment, let me know if you want me to teach a topic or solve a problem, and share with other people so that more people can have access to all this great learning. I bet it. that a lot of people use linear programming, people in business schools, MBA, and all of these things. So it's not just a science or maths kind of thing. Everybody in business and all these places, or even in manufacturing, in engineering, linear programming is useful for them. So do all of that, and I'll see you again. So watch out for the next video, which is going to be on some special cases for graphical solution method for linear programming. Till I come your way again, have a nice time. Bye.